Let us start this particular talk of single point incremental forming. And to start with, I will just give very quickly a glimpse of what are different types of single point incremental forming or incremental forming, I would say in general, and then we'll limit it to the single point incremental forming. So a couple of 3-4 slides will discuss about the IFP incremental forming process. Then subsequently we'll take the discussions on the what research we have undertaken at our institute and what are the findings. So to start with, let us have understanding of incremental sheet forming matters, which these are classical way of defining ISF incremental sheet forming. To name it, very first is single point incremental forming, whereas only one tool is moving and the defined trajectory, and then you deform the object, deform the sheet to require shape. That is called single point incremental forming, where you may not require to have a die. Without die also you can generate this required shape. Compared to conventional forming, in conventional we need some die support, we need some punch support, and then only you can get the required shape form. But in the incremental forming, where the moving tool, just like our CNC tool, which is having the cutting edge, whereas in the incremental forming tool is not having the sharp cutting edge, so it will not cut the object, but it will deform the object. And it is handle only, it is good to handle sheet of very thin dimensions. It will not be proper to have a bigger bulk forming. And if you have one tool on the bottom and one tool on the top, and tool can be called as a tooling also, where it is called two-point incremental forming, where one tool is supporting from the back, another tool is moving on the top, and one is from bottom, and thereby you generate the shape. It can be positive shape, it can be negative shape. When I say negative shape, means there is a cavity generated. And when we say positive shape, means there is some portion which is projected out. That is called positive incremental forming. You can see in the second picture, it is a classical image of positive incremental forming, wherein tools are used. One is called as a backup tool or a supporting tool, and another is the forming tool on the top. Similar, there is a more picture in the third figure. It shows again TPIF, that is again two-point incremental forming. But here, instead of stationary tool, we have a moving tool in the bottom also. So these are the different way of defining ISF. We will be discussing only for the first figure, that is called SPIF, single point incremental forming. There are some research going on for the TPIF also, but we will be limiting our discussion only for SPIF. Few more pictures will be good to understand. This is called as a hybrid incremental forming, where conventional forming is bundled with the incremental forming. Some work has been initiated at SVNIT in this line also. Professor Kumar is guiding the students on this work of hybrid forming, wherein the conventional die setup is used or punch setup is used. Not necessarily always it will be die setup. It can be punch setup also. And punch carries the object, and then the incremental forming can take place. So here the image is self-explanatory. You can see that the sheet is clamped in the clamping system, and then entire system is descent against the die. So sheet will wrap around the die, except the cavity will not be wrapped around. Only the dome portions or the top portions are covered up with the stretching of the sheet. And to get the forming of the sheet under the cavity, which is called negative forming, the tool is moving in the particular trajectory as particular tool path, and ultimately you will get the shape generated. That is called hybrid sheet forming, wherein the conventional sheet forming and the incremental sheet formings are combined together. There is one more case nowadays people are working with to handle some hard material which are hard to deform by the very thin tool, because the tool strength may not be sufficient to deform the object which are of a high strength. In that case, some heating has to be imparted before the forming, and that heating can be done by laser jets, laser supports, and that that makes the sheet little soft, and thereby the forming can take place. So this is the image of incremental sheet forming with laser supported heating system. Similar heating based forming is also done using robo system. You can see here from the one back side there is a heating system is there, and then you can have deformations from the front by using the 6-axis robo or maybe multiple freedom robo, and thereby you can generate the required shape of the particular object. So these are the different cases of the incremental forming. Few are advanced or hybrid in nature. There is one more which is nowadays used, but it is little under research, wherein you have to provide the entire system under heating environment, compared to the earlier picture wherein laser assisted incremental forming is discussed here. Entire system is heated, and thereby thereby material becomes softer, and then forming becomes easier, wherein the smaller tool also can deform the object which are of becoming soft in nature. So these are few points which I wanted to just introduce as a part of ISF, incremental sheet forming. But as I have stated earlier, we will be discussing on the certain investigations on the single point incremental forming in the course of our journey started almost 10 years back. Few results we could able to generate, and this I would like to share with you in the this particular presentation. This is a classical incremental forming picture wherein you can see the sheet is clamped, and then the forming tool, which is a small tool which rotates about its own axis as well as its revolve or its move on the particular trajectory, which is called as a tool path, and thereby it generates the layer by layer forming. When the tool descends further, it generates another forming layer, and likewise the shape of cup can be generated, which can be seen in this particular figure. There are certain process parameters which controls the successful single point incremental forming. These process parameters are named as a tool dimensions, which is called tool radius, as well as type of tool, maybe having what is the shape of the tool at the bottom, which takes part in deforming the object, or the tool touches the object, or tool touches the top of the sheet. So that shape is also important. Then tool travel speed, at what speed the tool is moving in the particular tool path, can be round path or can be any other different shape which you would like to generate. Then tool rotational RPM is also very important. Then the step size. Now step size has got two different nomenclature subdivisions. One is the step size in the planar dimensions, which is called as X and Y dimensions. What is step size? And second is the step size in the third directions. Usually step size is defined as a vertical tool movement, or the tool which is moving down after forming one plane of the sheet, because initial sheet is plane and then it takes the shape of the curve. So progressively every plane of the XY plane gets deformed, and ultimately you'll get the shape of cup. So this particular plane required to be defined in terms of step size, that is called dimensions in the vertical directions. So these are a few parameters. Even, of course, I missed out the two more parameters which are known as the wall angle. At what angle you would like to deform this cup. It can be 60 degree, it can be 50 degree, likewise. There are certain limitations in this single point incremental forming, that you cannot form the cup up to the 90 degree, or I would say it should be lesser than that. Then the forming height, up to what depth you can carry out the cup forming, means what should be the cup height. So that is what, these are the few parameters which are supposed to be the controlling the entire SPIF process. So let us start with the investigations of the various parameter effect on incremental forming. These are the few, again this is the same parameter list I have produced here. That is height of the cup or a cone, the radius of the curve, that is R, then Z is incremental depth in the Z direction, which is called as a step size. X is incremental step in X direction, because to generate the cup or to generate the cone, your every plane diameter should reduce from the major diameter to minor diameter. So to get this particular reductions in diameter, you have to have the step size in the x direction as well, and alpha is the angle of a cone, or angle of a cup. So these are a few parameters which are investigated here. To generate this particular profile, two profiles are studied here. The profile are, let me discuss that profile. That is the step size, step down. First, it takes the curve or the circular forming, and after reaching back to the starting point, uh, it moves down by the step down size, that is equal to z, and then step over size also is defined, that is in terms of the step in x directions, and that is how your contour is formed, or the cone is formed using contour by contour forming. Instead of contour forming, you can have a spiral forming only also, wherein the depth is given at one locations, and then continuously tool moves down as well as step over takes place continuously, simultaneously, I would say, and thereby you will get the spiral shape. So these are the two trajectory or strategy are studied in this particular research. So the various tool use are two tools. One is called hemispherical end tool, and second is the spherical end tool. So this is the hemispherical end tool, which is you can see the portions at the bottom. This is the hemispherical tool, and there is called near spherical tool. It is not 100% spherical, but it is near spherical tool, and there is a fixer used to grip the object or grip the seat. And this entire process is done on the CNC machine what we have in our institute, CNC milling machine, and that is sufficient enough to exert a force, because we are deforming seat of the aluminum material, so it will not require much force. So even the smaller CNC machine also can handle incremental forming. If you are handling little tougher or harder material, then it becomes a issue related to power of the machine. So this is the effect of the report result I am producing here, effect of speed of rotations on the surface roughness, because when tool moves on the particular tool path, it generates a tool mark, and this tool mark will give rise the surface roughness. So what should be the right RPM to be selected? So certain trial experimentations were conducted, and it is found that as RPM increases, your surface roughness improves, the surface finish improves, roughness goes down. So this is what one finding was reported, but still it has given some some school of thought that it is reducing, but still it will keep reducing. What will be the minimum you can get it, or whether the trajectory or trend remain the same or not. So study was further extended. So in that case, RPM beyond 1500 also was tried. So in that event, you can see the surface variations, and it is found that at a certain RPM, surface roughness found to be least among remaining other surface roughness. So one can make a choice that if you want to have a rotations to be given to the tool, what should be rotations to be given. So this is what one finding can be shared, that RPM should be not too high or should not be too low. If it is too low, local jamming might take place. If it is too high, it may result in excessive hitting at the particular locations, or it may have certain localized effect. So sometimes it is always good to have a surface speed of a tool moderately decided, so that the surface roughness can be achieved within the acceptable values. So similarly, we can have our discussions on the effect of feed rate. In the incremental forming, it is a slow process compared to the conventional forming. In conventional forming, only simply punch travel, deforms the object, and within very short of time, or with the minimum time, you can get the required object deformed. But in incremental forming, tool is moving as per tool path, which is already designed prior to forming. So it is time consuming process compared to conventional forming. So timing is also important, because ultimately it is related to the cost. So forming time control is one of the key factors. So here feed rate is the important parameter which controls the forming time. You can see when the feed increases, your forming time reduces, and that is but obvious. There is nothing to be discussed on this. But here two graphs are shown. One is with the Z travel of 0.5 mm, and then second is the Z travel of 0.8 mm. Those who have joined late, for them, just let me give again the understanding of what is Z. Z is the incremental depth, or Z is the depth which is given when tool completes one planar deformations, and to go to the second planar deformations, tool has to advance downward. So that is given as Z. If Z is less, obviously number of slices and number of layers are to be formed will be more. Hence, the time required to be formed for forming will be more. So higher the Z, lesser will be forming time. But at the same time, you have to balance what should be the Z. So to understand that, let me put forward this particular picture. You can see here two different Z's are discussed here. Well, you can see if Z is high, if amount of tool descent is more, you find the bigger material remain, which is called as undeformed material. Where here, if Z is slow or Z is small, you will find almost negligible left out material or undeformed material, which is shown as a delta H1 and delta H2. So these controls surface roughness, or these control the tool forming time also. So if you can see, if your Z is low, material deformation will be more controlled. If Z is high, material deformation will be less controlled. In that case, you will be able to notice that if Z is, these are the two pictures is presented here, which are the pictorial view of the actual experimentations conducted. We can notice that if you want to form the cup of same angle of 80 degree, which is at the same feed of 50 mm per minute, but if you have a different Z, Z is 0.5 and Z is 0.8, 0.6, you can notice that 0.5 is reasonably found to be safe compared to 0.6, where you find some failure is seen here. So this indicates that if you have excessive Z, that might result into some crack formations, and that is unadvisable or undesirable conditions. So it is always one has to balance as a researcher. If you increase the Z height, more chance of crack formations, but at the same time you save a lot of time in forming. But if you reduce the Z, less chance of failure, but increases the forming time. So you have to balance it. But ideally speaking, forming time can be controlled in terms of, because single point incremental forming is used as a prototype, or it is used just to have a study. Once you are done with your optimum combinations of parameters, you can nicely control your forming time to the best possible possibilities or options. So Z has to be controlled accordingly. So let me again put forward the different outcomes when Z is varied. You can see here Z is varying from 0.2 to 0.8, and for that the roughness are measured. As Z increases, your tool marks or tool serrations, or the serrations which are observed on the plane or the seat top of the seat, can be seen very clearly. Here, this is Z 0.2, almost there is a smooth surface. But as you increase the Z, your tool marks or tool serration is quite visible, and that increases the surface roughness. So you can see that as Z depth increases, the surface roughness increases. So it is advisable to have a lower Z value, so that surface roughness can be best or the better. But at the same time, if you increase the Z, not only surface roughness increases, but there is a chance of failure also increases. So this is how your Z has to be controlled. Similarly, there is one more study is done to understand the shape generated after forming. Here again, the study is done for the different value of Z, and this cup shape is measured with respect to the design or target shape. The blue line, if you follow the cursor, by chance, if you are able to see my cursor movement, this particular is a shape of this cup which is to be formed. But during forming, you will notice the cup will be formed like this. So there will be some error here. There will be some deviations in the wall, as well as there is some deviations here also. This you can see at the bottommost positions, there is a pillowing effect, just like our pillow. you will find the pillow at the edge will be having the lesser thickness compared to pillow at the middle. So this is called pillowing effect, and that pillowing effect adds some error in the SIP accuracy. So now here if you see the Z variations has got some effect as Z increases. Z increases from 0.2 to 0.5, you will find the formed component deviates marginally from the designed or target component. You can see Z.2 is reasonably closer or nearer to the target shape, and as you increase the Z, it advances, it goes away from the target shape. So it is, if you want to find out the accuracy as one of the criteria, Z should be set the lowest most value. But at the same time, you have to compromise with the forming time. So let us have the one more slide that discusses about the possibility to form the cup or cone, which is 90 degree. I should not use the word cone because 90 degree cone cannot be, it is a cylinder, it is not a cone. But still, we tried to form the 90 degree angle, but unfortunately, we failed in all the attempt. We tried to get the different diameter, smaller diameter to larger diameter, 15 mm to 24 degree. In each of these attempts, we could not successfully form it because 90 degree is really excessive forming, so it is not possible. So after this particular preliminary findings, we extended the study with the parametric investigations. You can notice, you can see the various parameters selected. Selected the RPMs from 750 to 1250, and feed rate was selected 75 to 175 with 125 sandwich in between. And then radial moment, that is X moment, was set at 3 different levels. Axle moment, shadows was set at 3 different moment values. And that is how the parametric studies was conducted. And in this parametric study, as your X and Z both are not the constant, these are varying, you will able to generate different cone or cone of the different angles. So this is the understanding of the cone angle, different cone angles. 45 degree to 69 degree, these are different cone angles can be obtained by varying the value of X and Z. You can see here X is varying is equal to 0.5 and Z is also varying from 0.5. You get 45 degree angle. But if you vary Z more, 0.8, and X less, you will get some different angle. So this is what the understanding of a geometry, what at the end of the forming, which type of geometry can be generated. So this is the results produced for all the total 9 set of experimentations was done. Orthogonal array, Taguchi orthogonal array was designed, and it was L9 array was used. And the speed, feed, and then the X and Z were varied as per the orthogonal array L9. And the angle of cone which is produced after deformations, and height of the cone which is produced after deformations, and what is the forming time are recorded, and the errors are tabulated here. We can notice that the value of Z, which is 0.8, is not that way visible so far as the value of speed is high and feed is moderate, which is shown with the red color. Otherwise, all other 8 samples could be able to be generated, and that error was reasonably less because target angle and the achieved angles are really in close agreement, except in 1 or 2 cases where there is a little more error. But successfully, we could able to form this component of a cone shape. Then we did the focus experimentations, some detail experimentations. Again, the same parameter was studied, but here the another parameter was added. That was a wall angle. Wall angle was added compared to the earlier case. And here 3 different strategy of a tool path and the tool shape combinations was introduced. These strategies are defined as a hemispherical tool. Tool is of hemispherical nature, but it moves on the contour tool path, means circular nature. Similarly, hemispherical tool between spiral tool path. Then spherical tool in contour tool path and spherical tool in spiral tool path. So these are 4 different strategies. Out of these 4 strategies, 3 strategies were used for the comparisons, just to understand what works out to be best. So this is what the results, what we got it. Sorry, it got stuck somewhere. Okay. So these are the results. I think I have discussed this, so I will just skip further. And this is the combinations of the optimal parameter findings, which are shown here for different strategy: hemispherical tool with contour tool path, hemispherical tool with the spiral tool path, and the spherical tool, the spiral tool path. These are the few findings, and after this finding, it was found that the C and D, these are the parameters which are defined as the depth angle and then the incremental depth. These are the few governing parameters which are considered a significant parameter. Then some accuracy study was also done, profile accuracy study was also done, and the thickness measurement was one of the important aspects of the forming was also taken up. You can notice here that to measure the profile accuracy, total at different locations, 46 locations, measurements of the profile was taken, and then it was plotted to get the shape. This is the shape what we could get it of the one of the profile I have presented here. There are all the samples profile were recorded and compared. So this is the table shows the variations or the error with respect to the profile error. Two different trials were done, and the average profile error here out of 46 readings, what is the average is recorded in each of this particular row. An average of each of total 9 readings are recorded over here, and from here one can make a comment that the average of the profile error of HST-CTP means hemispherical tool will contour tool path found to be the least compared to the average error of profile accuracy of other two trajectory. So HST-CTP is used for further study for the investigations of various parametric effect. Being profile accuracy, we could able to get the variations in profile at 2 different places. You can see this is already discussed earlier, but still I would like to project it again. The orange colors is the target geometry or design geometry, and then this is the form geometry. This is the form geometry. If you see here the form geometry, this line which are shown with the different colors, you will find that at the wall it is almost on the target geometry, but it deviates much as you move towards the edge of the die or edge of the holder, blank holder, and at the below you will find this is the variations. So this is also one of the important parameter that average may be favorable, but the localized error might be a point of concern. So one has to balance, one has to have a common factor. What is the main criteria to be kept as a one decision making criteria? If it's average error, then hemispherical tool with this spiral tool path, or sorry, contour tool path is okay. If it is here, that is the HST-CTP. If it is, if you want to go with the localized error or deviations, you'll find here deviation is more, here also deviation is more. But in both the case, you'll find red color. Red color is close to your target geometry. Red is got HST-CTP, means hemispherical tool with contour tool path. So contour tool path gives you less pillow error. It gives less corner error. Here it is almost same, but here on the wall, error are all the different strategy has got almost similar path or similar shape. This is what the study of thinning is done. Thinning is done by measuring the thickness at the various locations. This thickness is measured comparing the thickness of the original sheet. It is almost 0.9 mm. And after deformations, the cup take this shape, or sorry, the thickness variation take this shape. It is not the shape of the cup, it is a thickness variations right from one corner to another corner, right from the on the wall as well as on the bottom also. This is the distance from the axial path or the axis of the cup, and you will notice that the formations or the thinning is varying minimum to the flange, and it increases on the wall, and it further increases, and thinning become the maximum at the corner of the band, and then again it rises on the other side. This green line indicates the cosine or sine law rules, based on which also you can find out the thickness that is constant, assuming is a constant. Actually, it is not remaining constant. We shall see in some other discussions as well. So this is what the thing analysis, and then we have decided to carry out further investigations. This is done with the tool strategy. Again, tool is same, contour, hemispherical tool, but contour and spiral tool part only is taken. Spherical tool is not considered here, and the parameter which was added here is the target height and target height and tool diameter. Tool is change of different diameter, and then the study was reported. So this is what the shape what we got it. Already we have discussed, so I am not taking much time here. In the earlier case, total 46 readings were taken. Here, 106 readings were taken to generate the profile in a better accuracy. And the one can see that the shape almost are similar for the HST-CTP and HST-STP. That is called contour tool path, and the spherical tool path with the hemispherical tool. These are the some experimental pictures obtained at different angles. In the present study, at 90 degrees was not possible. 90 degree was not possible. Here, 80 degree also has failed in some of the sample, which was simulation number or experimental number 8, which has failed. I have already presented that particular result in one of the earlier table. And this is the straight failure at 80 degree, you can see. And this is a failure which is called zigzag failure at 80 degrees. So these are different types of failure you can notice in the incremental forming. This is a corner failure, you can see on the wall. This entire edge is failed, just similar to the similar findings reported by Surat in 2012. So these are the few pictures, glimpse of the failure. We did some empirical modeling also of profile estimations, and these are the results of the model, where regression model is used and compared. Here in this particular model, 75% readings are used to develop model, and 25% readings are used to compare the model developed. And that is how you can see the model readings are shown with the blue color, and experimental readings are shown with the red color. These are bound to be in good agreement because these regression models are developed using the experimental data itself. So these are a few same results of the profile error with the incremental depth of the different feed. There are 3 different feeds investigated: 75, 125, and 150. Even 225 also, yeah. So these are the 3 different feeds we tried, and we could able to compare. One very useful information one can gather from here is, as your the feed increases, if I put forward again the same, if we increase the feed, say this feed is 75, the profile error is somewhere in range of 0.3 to 0.4. That is a root mean square error. But as soon you increase the feed to 150, error also rises from 0.35 to 0.5 onwards, and here it further rises to 0.5 to 0.65. So this what is the takeaway, that as feed increases, your error also increases. Hence, it is desirable to keep the lower feed, and that is also discussed earlier. It increases the accuracy, but at the same time it increases the time of forming. So this is what I already discussed. What a remark I'm presenting here, these are already covered up, so I'm not reading line by line. So I'm just scrolling these particular slides. Then we did some, this is very useful and latest ongoing research, and few might be having some interest in this. After doing successfully incremental forming of a sheet that is made of the homogeneous material, which is made of the single material, we did we did carried out some investigations of a tailor welded blank. So tailor welded blank is what? It is a blank which is welded prior to forming, just to have a economic in the manufacturing in terms of cost saving of material without much compromising the strength. And usually it is having found some applications in automobile industry where some portions require some high strength material and some portions are only required to support the things. You can compromise with the material strength, you can compromise with the material types, or you can compromise with the material thickness, and thereby you can use material combinations or thickness combinations which can be called as a TWB, tailor welded blank, and these blanks are welded prior to forming. So obviously, when you are introducing the welding process in between these two material, the property behavior, material behavior changes, which is unlike what you find in the conventional or even the incremental forming of an ordinary sheet, which is made of same material having the same thickness. So here, the study is attempted focusing the factor of material property on the incremental forming, as well as tool initial positions. What is the effect of tool initial positions on the incremental forming? That is what the target of this particular investigations. So here the study was done where the material property is varying. That is K and N. K and N are the material property. K is a strain coefficient, N is a strain handling index, and the combinations of a two, where here two materials are welded, assuming that the strain ratios are varying. Assuming that one material is constant, so it is 0.125, another material strain index changes. So thereby your two materials which are welded will have a common N ratio, similarly common K ratio and thickness ratio. Here it is assumed that material will be welded of a thickness 2 by 2 or 2 by 1.5 or 2 by 1.25. That is how different thicknesses are considered here. Similarly, strength also having the different values, 200 by 200, 200 by 175 megapascal, 200 by 150 megapascal, and these are the ratios. Here, there is the concept of defining thick material and thin material, or stronger material and weaker material. So what is a thick material? Thick material means ratio or the material thickness which is higher. Is a thick material. Material which is of a lesser thickness, it is thin material. So based on thickness, one can make out that if material are same for both the material, based on thickness, you can say that thicker material is a stronger material and thinner material is weaker material. So based on thickness, you can always define strong and weak material. Similarly, you can define the strong and weak material based on the yield strength also. Higher yield strength is called stronger material, lower yield strength is called as a weaker material. So here, the attempt was made to have a study of combined effect of thick to thin material and strong to weak material behavior in incremental sheet forming. So the study was focused for the different tool starting positions. This is a pictorial view of the material which is welded. The gray color or blue color is shown with the strong combinations, and these are weak combinations of weak material, and in between there is a red color patch which is known as a weld dimensions, a weld zone. This is a simulation study. We did finite element analysis, and for that the weld dimensions were assumed as the weld zone dimensions based on the literature. It is around 6 to 8 mm thickness or width of the weld was assumed, and you can see 4 different tool starting points was considered here. This is the call as SC point. SC stands for tool starting from the center of the strong material. Here, tool starting from center of weaker material. This is tool starting from the weld itself and moving towards weaker material. And here the tool is on the weld itself, but it moves in this towards the stronger side. Now, what is the effect of this? Yes. Yes.
That was by mistake, sir.
Okay, okay, okay. Fine. So this tool starting point has got some importance here, because if you go with a contour tool path, tool will move at this point, tool will start from this point, and first incremental depth is given in the z directions, and at that depth tool moves in a circular fashion, like this. If you follow my cursor, it will move circular and complete one planar movement, and after it completes one planar movement, tool again given the depth by that incremental depth of say 0.5 or zero point 0.6 or whatever is set for, and then again second contour is generated. Like that it goes down 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 to get the required shape. So this is what the importance of starting point. So means at every starting point, tool descends downward. So it has got some tool mark effect here. Here tool descends at the weld line. So weld line will have a tool marking. So this is what is the plan to study the effect of this tool initial positions. This is the combinations of the parameter which was already shown here. These are the three levels of four parameters. Combinations L9 was generated and this was used, and this is the shape of the geometry which was targeted. Angle of geometry was 45-degree, and then the cone of radius 50 as a top diameter, and the bottom is 10 diameter, and that is how height of 20 was generated using contour tool path. Contour tool path was already discussed earlier. So I'm just showing you the that particular picture again. Step down the Z travel in the downward travel, and step over to get the required angle of 45-degree. So the tool parameter was set as the radius of a tool 6 mm. Then friction was assumed as 0.1. It is simulation study, so some assumption is required. Then the incremental depth was taken as 0.5, and then rotation speed was taken 1000, and travel speed was, that is a field, was taken 15 mm per second. So let us understand the results. Let us read, understand, and interpret the results. This is the pictorial view of the shift of weld line. There is a peculiar phenomena taking place, especially in the forming of tailor-weighted plank. Tailor-weighted plank, as we know, it is a mix of welded portions of weaker material with stronger material. So whenever there is a weaker material and stronger materials are welded, the deformations behavior of both the material will be different for the same amount of loading. When the deformation behavior is different, weaker material will have a tendency of more deformations compared to stronger material. Hence, the weld line, which is earlier before deformation was kept at the center, will no longer remain at the center, but it moves. It moves marginally. So you can see here that the weld line is moved, and you can very clearly see the displacement or shift of weld line. And it is because of the weaker material that has more deformations, and stronger material have less deformation. So this is the one of the important drawback of this TWB forming. And researchers are always trying to control this weld line shift, especially for TWB, so that the property can be uniformly distributed along the deformed object. So this is the objective of study. Now, when we carried out the study, this is the simulations results. Weld line is shifted. This is what the arrow, pink, yellow arrow indicates the shift of weld line. This is a tool movement, and tool starting point is shown with this dot. This is a stronger material, is a weaker material. So weaker material will have more deformations compared to stronger material. So you'll find some deformations of the weld line. Now, the reason of weld line shift has to be understood. It can be well understood from this particular figure. This figure says that the tool starts from this point, and it's moved from the stronger this weaker material to stronger material. So when tool moves from weaker material to stronger material, tool is starting from weaker center point. We can see WC is a weaker center point. This is the point which is pressed first, or this is the point where deformation takes place first. And then deformation moves towards the weld line. So deformation direction is towards the weld line. And at the same time, tool is also moving in this manner. So the tool which will be in contact with the surface of the top of the work sheet, the sheet which is in contact with the tool bottom point will be dragged because of tool motion. So workpiece or sheet will be dragged marginally because of friction between tool and the workpiece. So because of that also the weaker material will have a more deformations, and that can be seen that if I divide this particular entire deformation zone, I am dividing into two different zones, A and B. In A portion, because of direction of tool motion, the deformation can be visible. But soon it crosses and it starts deforming B area or zone, which is B area. You will notice that dragging will be towards this tool motion, means it will be upward. But the deformation of the weaker material will be always downward. So because of that, it will compensate the deformations, or it will compensate the weld line shift. And that is why you will not find much weld line shift here, but you will find much weld line shift in this particular zone. So direction of tool motion is very important. Direction of tool motion is important to understand the weld line shift. You can very well notice this. These are directions, and here only you find the weld line shift. You do not find weld line shift here. So this is what the first takeaway, that important of the starting point and important of directions. It can be further related in advanced or bigger scale. Just what I have discussed earlier, same is projected here. You can see that this is a weld line prior to deformations, and then this the blue line is shown as weld line movement or displacement after deformations. This green arrow shows the contour tool path. It starts from weaker area, it moves towards weld line, and it goes towards the stronger area, and then again it is returning back. This particular brown arrow indicates the deformation of weaker material, and this blue arrow indicates the deformation because of the tool dragging. Tool dragging also adds the deformations. Here tool dragging opposes deformation. That is why deformation is less in this zone compared to deformation is bigger in this zone. So this is what is observed in almost all the sample what we have tried for different combination of the factor and level of L9. We did the study for all different 4 starting points. SC stands for strong starting point, WC means weak starting point, weak center, WTS means weld too strong, then WTW means weld too weak, means starting point is on the weld and tool is moving towards stronger side. Then starting point is weld and then it is moving towards the weaker side, and combinations of results are tabulated here. It is found that almost all the simulation reading out of 9 set for each of these trials. So total 36 trials we did. Each starting point 9 trials. So out of that 6 trial number or the explanation number or simulation number found to be the giving the minimum weld line shift, minimum thickness, thinning I would say, not thickness, minimum thinning. Minimum thinning is desirable, minimum thickness is not desirable. So thinning has to be minimum. So this is what it is found that among all 4 comparisons, WTS means starting point is on a weld, tool starting point is on a weld, and tool is moving towards stronger side, will result into the minimum weld line shift as well as minimum thinning. So this is always desirable. When forming of TWB is to happen, it is always desirable to have a minimum weld line shift and minimum thinning. So if you want to control the minimum weld line shift and minimum thinning, you must choose the tool starting point on the weld portions, and tool should move towards the stronger side. So this is what is the finding, except for one case where the finding is little change, but that can be ignored. So you will say out of total 18 such samples are shown here, or it is found that 12 samples are shown here. All 11s are in the agreement except 1. That is acceptable. Then you can see the various combinations, effect, contributions of various parameters for every starting points, all 4 starting points, SC, WC, WTS, and WTW. And it is noted that out of 4 parameters investigated, index, strain index ratio, strain coefficient, thickness ratio, and yield strength, it is found that the thickness ratio is highly contributing to deformations of weld line shift, as well as the yield strength ratio is also contributing, or these are, I would say, significant parameter compared to the strain index and the strain coefficient. These are not much significant, but these 2 are very much significant. So if you want to have minimum weld line shift, you must have control on the thickness ratio, you must have a control on yield strength ratio. Similar is finding for WTS and WTW also, well too weak and well too strong. And this indicates the optimum combinations. Optimum combination is shown here as, I'm just getting one, as A-1, B1, C-1, D-1. What does it mean? It means that the lower level, that is a thickness ratio should be say 1, yield strength should be 1, means it is nearly homogeneous conditions will result in minimum line shift. Means soon you introduce deviation in thickness of two different material, well line shift is bound to be there. Soon you introduce variation in yield strength, say well line shift is bound to be there. Higher the ratio, more will be well line shift. Higher the thickness ratio, more will be well line shift. Hence, to control the well line shift to the minimum, you must have a thickness ratio should be 1, yield strength ratio should be 1. Thinning also results in a similar picture. So percent thinning can also be controlled by controlling the strain thickness ratio as well as yield strength ratio. So this is what the preliminary analysis. We have some thinning analysis also. These are the simulation picture. You can see here simulations pictures of all four conditions, and this indicates the failure. This is the veil portion, center portion orange color, then red color, and on the other side on the green color there is a you will find a dark blue line indicates the failure line, because of the veiled portions and thin portions are separated by this particular edge. So this is considered as some weaker area, and that has resulted in failure. This is a failure because of tool dragging or tool indications. Tool is given first travel from this point, and every point it has got some deformation. So that is why you have a tool marking, and that results into the thinning. Similarly, here also you will find the thinning on the edge of the veil and the thinner material. Here also will find a similar thing. There are two different failure edges you can see. So these are the images of these simulations. This is for the simulation number 3. This is for simulation number 6. I'm just skipping this. It's just only to show you the image of the findings of simulations. Then we did the comparison of geometry also. Geometry comparisons are based on the tool starting point. 4 different tool starting points again are compared for the shape of the geometry which are obtained, and you can notice that the shape of the cup which is formed deviate much if it is measured orthogonal to veil. Here it is a tool starting is from the strong center. When tool is starting from strong center, obviously it is orthogonal to veil. So being orthogonal to the veil, first deformation takes place orthogonal to veil, and that is why it is little bit deviated, where the shape of the cup along the veil is nearly coinciding with the shape of the target geometry. Similarly is observed for the weak center also. Weak center means that is orthogonal to veil, and orthogonal to veil is always deviated little bit, and then this along the veil it is following the particular shape of the geometry. If you take the similar conditions for WTS and WTW, means veil to strong and veil to weak. Here tool is on the veil. Tool is on the veil. So along the veil, tool is deviated, you can see. And the across the veil, means orthogonal is always to the accuracy. Means the takeaway here is the shape of the cup which is formed, keeping the tool orthogonal to the measuring plane, then the deviations will not be there. But if it is deviation is, or if geometry is measured on the same plane of a tool initial starting positions, deviation is much there, is much higher. So that will give you some useful information that the tool starting points is governing the overall this, not only the well line shift, but also it controls, or it's govern the shape accuracy also. So this particular study was further extended. What is extension of this? We have attempted to study the various angular positions of a tool as a starting point. You can see here These are various angular positions we have discussed. Strong center starting positions. These are whale starting positions, whale to strong, whale to weak, and in between three more starting points are considered at angle of 30 degree, 15 degree, 15 degree again. So this is a 0 degree if you're assuming strong strong center is a 0 degree, then 30 degree is a second point, then 15, then again 15, again then 90. So these are the 5 readings are taken, and we try to overlap the measure the shape. You can see here that tool starting point is a strong center. As a tool starting point is a strong center, and weld is measured normal to weld line, means geometry is measured along the tool starting point, strong center. It has deviated much. It has deviated quite a lot. But as your tool starting point is moving from strong center to 30, 45, 60, and then WTW or WTS, the deviations of the tool or the form geometry from the target geometry is reducing. You can see it is a target geometry and deviation is reducing, means it is desirable to have the tool starting point effect to study. Now, another takeaway here is, if this dotted line is the target geometry, and with respect to this target geometry, these two lines that is called as a WTS and WTW are reasonably in close proximity or in approximations compared to other angles. So it is takeaway is WTW or WTS is the good point to start with the forming of the TWB. We did some investigations of individual parameter as well. These are the glimpse already we have discussed. The thickness ratio and yield strength ratio are more significant parameter. That is why you find lot of weld shift when you take the thickness ratio and the yield strength ratio. Similar is the finding for the percentage thinning as well. Percent thinning also increases as your ratio of thickness and the ratio of yield strength increases. This is the study which shows the effect of lubrications. This is the effect of lubrications. Two different lubrication conditions are considered: low lubrications and higher lubrications, or lower friction ratio and higher friction ratio. So when you apply lubrications, friction coefficient will be less. When you have a no lubrication, friction coefficient is high. So two different friction coefficients are studied here, and it is observed that as the friction coefficient is less, the weld line shift is less. As friction coefficient increases, weld line shift increases, and that can be well understood by this particular figure based on tool dragging directions. This yellow arrow indicates tool dragging, and this tool dragging contribute to the weld line shift. Stronger material, weaker material will always have some contributions, but you can see if I divide it again, these two portions, this upper portion is stronger material, lower portion is weaker material. The deformations of the weld line shift in both the case of lower friction and higher friction of weaker material is more than stronger material. You can see here the weld line shift is observed to be 1.5 mm, where here it is around 1.2 mm or so. Here it is 1 mm for a lower friction, and here it is 0.4 around for lower friction in the different area of A and B. Because of tool dragging effect, this tool dragging is contributing towards the weld line shift of weaker material, because weaker material will have more deformation compared to stronger material. That is why you will find more weld line shift in the zone B compared to zone A, because now tool dragging is opposing your weld line moment of a weaker material. So weld line moment or tool dragging is here is less, and here it is more because of the weaker material have a more deformations. Here weaker material the deformation is less. So this information helps you to find out the effect of lubricants, and it is advisable to use certain lubrications so that the surface roughness also can be improved. Weld line shift also can be controlled, because if when you compare these two graphs, you will have noticed higher the coefficient of friction, more is weld line shift. So to prevent the weld line shift or to control the weld line shift, you must use some lubrications. So then to estimate the strain, actually our focus was to have a FLD analysis also. We did some grid marking on the sheet, and we did study the effect of grid marking, types of grid marking or process of grid marking on the overall performance. We marked the grid using the ultrasonic UV marking as well as laser marking, and we did the comparison. It's found that the ultrasonic UV marking, I would say, not ultrasonic, UV marking resulted into the more forming height. Means it is desirable, it is advisable. And also it has deformed the safer geometry compared to laser grid marking. Laser grid marking actually reduces some fine material which weaken the overall strength of the sheet, and that is why failure chances rises. And that is why you can notice here that the F indicates the failure, S indicates is successfully formed. So the blue marking, which is UV marking, could able to form the geometry successfully, where orange marking, the laser marking, has shown some failure. So the takeaway here is that to carry out the forming limit diagram analysis or forming limit curve plotting, grid marking, if you are targeting, the grid marking should be done using UV marking rather than laser marking. So this is again the similar picture. I am not discussing much on this. We will straight away go with the effect here. These are the UV mark samples which are formed in our workshop, in our laboratory of different thickness, 0.5, 1. Then these lower two figures are the laser mark object, again for 0.5 and 1. And you can notice the tool marks here in all the four figures. This first figure indicates tool marking, which is having the tool marking because of starting tool positions. And these are during the rotation of the tool, there are some tool markings. Then we did the for FLD, we plotted the FLD, and it is observed that the FLD plotted using the ultrasonic mark sample, which has resulted in a minimum strain or lesser strain, which can be seen here. This is the triangle shown the safe UV, ultra UV marking, and this rectangles are shown as a laser mark. And if you compare the strain values, this is a major strain, on this axis is a minor strain. To plot the FLD, those who are familiar with FLD, they will appreciate this particular curve, and you will find that the strain of the UV mark sample is always less compared to strain of the laser mark sample. And higher the stress, higher strain, higher will be stress. Higher will be stress means chance of failure is high. So we did some explanations again. I'm just skipping these slides just to make up our time, what our time loss. These are the few explanations what we have conducted. This is what the shape of the tool we have used. Hemispherical tool was used to carry out the control tool path rotation. This is the sample shown here, which shows the tool motion and the tool dragging effect, and then weld line shift after deformations. And this is a tool starting point. This is done on the weld itself. This is WTS conditions. Tool is started from the weld, and weld line is shifted in this manner. This arrow indicates the tool motion in the counterclockwise directions, and the weld line shift are compared for 4 different combinations of the thickness and feed. Here thickness are taken as P and Q are of 1.67 thickness and RSS are 1 mm thickness. Feed of 14.828 mm per minute, and combination was studied here. It is found that the weld line shift is highest for the lesser feed and the thinner material. Why it is so? Because lesser the feed, more time tool spent at the particular locations. Hence, it will try to take the material along with the because of friction along with the tool rotations, and we try to drag the material more, and that eventually result in more weld and shift. If you take the similar conditions here for the same feed, your feed is same for Q and S, but as thickness is less in S compared to Q, Q will have a lesser weld and shift because it offers a resistance of deformation, being a stronger material. As I have already introduced earlier, higher thickness is considered stronger material, lesser thickness is considered as weaker material. So weaker material will have a more weld and shift, stronger material will have a less weld and shift. Again, feed is also considered here. Higher the feed and lower the feed, these are two are compared for the given experimentations. But it is not much variations for the P and R because the feed is high. So this is what the image what we could able to obtain. There is some failure also is seen here, and that failure is on the weld itself. There is a sequence of welding. Please understand, this welding is done not by the conventional welding, it is done by friction stir welding process. And the friction stir welding has got certain particular conditions that there are certain issues related to weld strength. You will not find the uniform weld strength because of the process limitations. So friction stir welding, you can always correlate here. It has got the opening of weld. You can see this opening of weld on the corner. Here also it is opening of weld. This is also some samples which are showing the opening of the weld. You can see opening of weld. So these are few failed component. Few safe component also are deformed. You can see the right top figure, that is a safe component which is formed. Though tensile strength is low, you can see tensile strength of weld is low. Here tensile strength of weld is high. Here it is a maximum 107 among these three. But still there is a failure here. Still there is a failure here, but it does not have failure here. Might be the reason is the uniform distribution of weld property along the entire weld line is a matter of concern. Here, though the localized strength may be there, but still it is failing in the incremental forming. So in incremental forming, the weld strength is another parameter which is to be point of concern while deciding the various operating parameters. This is the comparison of thinning done for the different combination PQRS test, and here three different trials are shown here. You can see this is the blue color column bar chart are the thinning values, percentage thinning values obtained based on experimentations. In that, the thinning thickness at various locations are measured and percent thinning was plotted, which is maximum. This orange color chart, bar chart, is a thinning calculated based on the limiting thinning concept of the concept of tensile instability. In tensile instability, material behavior becomes unstable once it reaches to the ultimate strain. So ultimate strain was considered as a limiting conditions, and based on the ultimate strain of the given material, the percent thinning was obtained. Here, the percent thinning was as thickness is same. P and Q has got the same thickness of 1.6. R and S has the same thickness of 1. Thinning is same. You can see 16.56. Both are same. Here 18.70. Both are same. Then sine law. Sine law is based on geometrical trigonometry, wherein the cup angle is known, thickness of the sheet is known. Then you can find out thickness. Final thickness is equal to T0 by sine phi or sine alpha. Sine alpha is nothing but the alpha is angle of the cone, and T is the final thickness, and T0 is the original thickness. So you can see that the percent thinning is more in case of single incremental forming compared to the percent thinning obtained using tensile testing and percent thinning obtained using the sine law, which is empirical in nature. So these are the bar chart of all safe deformed object, not the failed object. So please understand that these are all objects are safely deformed. This is surface toughness values obtained for the combination of 1 mm thickness, 1.6 mm thickness. In the process of deforming, dummy sheet concept was also used. One sheet was kept over another sheet because the elevated blank teeth will be has got a weld portion in between, and this weld portion might offer some restrictions of tool motion because at some point that weld portion being a larger or bulky area which might prevent a tool smooth contour path. Hence, to prevent that, dummy sheet is kept over the sheet of the deforming object, and then the thickness was the surface roughness was measured. As a dummy sheet is kept between the sheet which is undergoing deformations and the tool, there is no direct contact of a tool with the deforming sheet. Hence, the surface roughness is very good, or I would say surface finish is very good when dummy sheet is used. So you can see the red color is a surface roughness value using dummy sheet, and blue bar chart is a surface roughness value without dummy sheet. So where you can notice the surface roughness is high when dummy sheet is not used. The thickness 1.6 mm result in more surface roughness compared to 1 mm. That is the reason because the 1 mm surface roughness offered less resistance. Hence, no much load is required to deform it compared to the 1.6 mm. Larger the load, more will be the punch or the tool deforming the object, and that will result in the more surface roughness. So this is what the surface roughness, the effect of lubrications was discussed, and then FLD was plotted. I will just show you the FLD final experimentations of different surface roughness value. I'm just skipping this, and this is what the FLD what we have obtained of different conditions of a tool starting point with lubrications and without lubrications. You can notice here that these continuous line are the line indicating the without lubrications, and these dotted lines are the picture results shown with lubrications, and the strain value, major strain value and minor strain values are less in the lubricated conditions compared to the non-lubricated conditions, and which is desirable or advisable phenomena. So one should always provide some lubrications when you are dealing with the better surface finish as well as the better deformations or better formability. This particular chart also indicates the formability also. Higher the strain, that chances of reaching to the failure is more. Lower the strain, chances of reaching to the failure is less. Hence, it is having the more chance of deforming. You can go further depth to achieve the more height of the forming. So this is what the FLD of the particular experimentations. Tool listener position already we have discussed. These are few results experimentally obtained. I am just showing experimental result as a only glimpse of the picture. Earlier result was for the simulation findings. These are for based on experimentations, and you can see there is a well line shift. There is always a tool motion which are favoring or opposing tool well line shift. These are few pictures. It is just for your understanding and correlating your experimental finding with the simulation finding. You can see here, these are the few experimental results. And similarly is the well line shift obtained. And here it is noted that well line shift in WTAs is minimum, which is also in agreement with well line shift obtained based on simulation. WTAs always give minimum well line shift compared to remaining starting positions. So starting position is a matter of concern, and one should always try to keep the tool on the wheel itself. And wheel being a stronger, harder material, you need to have some annealing also, heat treatment also. That is the added process to handle the strength of the wheel portions and capability to have a more formability. This is the another picture showing the direction of the deformations. If a tool is on the wheel itself, the action will be along the wheel. But if tool is orthogonal to the wheel line, the action will be orthogonal to the wheel line, and that will eventually deviate your final shape to the target geometry. This is already discussed in simulation results. I am just showing you the few results what we have obtained. And this is again FLD. Here FLD is plotted comparing the TWB with the basic material. Welding is done using two materials. aluminum 6061T6 and aluminum 50830. These are the two materials welded, and then single point incremental forming was done. In SPIF, you can notice that as you introduce the welding in the material, the basic base material has got the safer deformation. You can notice here. But soon you introduce the welding, the material become difficult to deform and chances of failure rises. So you can see the SC means strong center has got the very high chance of failure, and the WTS, that is shown with the green color, is less chance of failure compared to remaining three starting positions. But if you have a single material without any welding, the failure is still lesser. You can see here. But soon you add the welding, the material become harder. You have to carry out heat treatment, and then because of welding itself, the material has got some discontinuity, and that will also result in straining, rising straining, and that is why all the TWB experience more straining compared to the straining of the base material. This is again the comparisons what I have already shown using limiting thinning dimensions and sign law. This is what same, and then the surface toughness was measured at various locations. This is what the picture is showing. So let us have, this is what the measurement of force done using extremities, force measurement, and you can notice here that these two base material experience less force. You can see black color and orange color are the less force, and green color require more forming force. Because it is a TWB, it is having some welded material in between, hence the material require more load to deform. So it can be seen here. There is a force measurement done at our laboratory, and this is enlarged portions of this particular figure. It takes some time to load that particular figure. You can see this black color is a single material, and red color is another single material, base material, and the green color is a TWB. If you compare these two, you will find that the force requirement of welded material or the TWB is always higher compared to the force requirement of the base material. And second, here you would have noticed that in the one planar moment, this is one planar moment, means this is a starting point and it moves contour tool path and again come back to the starting point. Again, second path, third part, like that, it keep moving. So it is a sine wave type of nature, and you will see that force rises up to some point, then it drops. So this is a weld process. This is a weld material. And a weld material, you are giving some increment, you are giving some depth. As you are giving some depth, material motion, tool motion is ceased for a while. There is no tool motion at that point because you are descending the tool downward. When you are descending the tool downward, there is always a load which is calculated based on the incremental depth only, and then again remaining material has to be moved, has to be deformed along with tool motions. That is why there is a variations of the force you can notice here. So this is what what I have discussed. Then few more slides are there, but these are not the part of the single point incremental forming. So I think I'm done with this. I'm stopping my presentation here.